I made an impossible puzzle. Not impossible as in very hard, but actually not possible. So what's going on? To me, it looks very normal, very innocent. And comparing it with a regular sliding puzzle, there doesn't seem to be a difference. Both have 15 tiles and a vacant space. But when we start to solve them, strange things happen. Our regular sliding puzzle solves easily. Nothing too fancy, we solve first row, first column, second row, second column, and we are done. But our impossible puzzle puts up a fight. With the same approach, we are so close, but the 11 and 12 tiles are switched. If we make moves to fix 11 and 12, suddenly 14 and 15 are switched. If we make moves to fix 14 and 15, suddenly 9 and 10 are switched. No matter how long I tried, there always seemed to be one pair that was not correct. But this incorrect pair might be the key to what makes this puzzle impossible. Let's say an interchange is two adjacent tiles that are swapped. A solved puzzle has 0 interchanges. Everything is where it should be. In our regular puzzle, if we rewind just a few moves, our puzzle has 2 interchanges. If we go all the way back before we made any moves, it looks pretty random. But strangely enough, if we solve it with interchanges, it totals to 24 interchanges. See the pattern? It's pretty strange that 0 to 24 are all even numbers of interchanges. Well, let's go back to our impossible puzzle. I remember being so frustrated that no matter what I tried, there was always one pair of incorrect numbers. Because we are thinking with interchanges, we could say that we're stuck with one interchange. When we rewind our impossible puzzle all the way back to its original state, and we solve it with inversions, we count 33 inversions. 33 is an odd number. It seems like we're onto something. The pattern shows even inversion puzzles can be solved, and odd inversion puzzles cannot be solved. This seems like a nice conclusion, but we're guessing the pattern. Let's prove it. Woolsey Johnson in 1879 published a proof on the solvability of a sliding puzzle. He says, step 1, remember our vacant space. Okay. After some n moves, followed by a direct transfer from our previous vacant space to our new vacant space, the board could be described with n-1 interchanges. Okay, so what does this mean? If n equals 2, we make 2 moves, okay, followed by a direct transfer from our previous vacant space, I remember this was position 16, to our new vacant space, which is position 14. This board could be described as having n-1, so 1 interchanges. And this is true. Okay, what about n equals 5? So we make 5 moves, we make a direct transfer from our previous vacant space, position 16, and we make it to our new vacant space, which is position 5. This board could be described as having n-1, so 4 interchanges. And it does. Okay, what about when our moves are not in a line? We make our 7 moves, we make a direct transfer from our previous vacant space, position 16, to our new vacant space, position 13. This board could be described as having 6 interchanges. Nice. Okay, so step 1, Johnson said n moves, direct transfer, n-1 interchanges. I am convinced. Step 2, after n moves, if the vacant space is a gang left vacant, the displacement produced might have been produced by n-2 interchanges. Okay, what does this mean? Remember that part 1 says n moves and a direct transfer is n-1 interchanges. So, saying n moves with no direct transfer is n-2 interchanges, well, this means that if it's a loop, so if the vacant space does not change, the last move is the same as our direct transfer. Is this true? For a small loop, let's say n equals 4, when we make a direct transfer, it is the same as our last move. Okay, so after the first 3 moves, we make a direct transfer from our previous vacant space, position 16, to our new vacant space, position 12. Is this the same as our last move in the sequence? Well, it is. Okay, so this n equals 4 sequence might have been produced by n-2, so 2 interchanges. Okay, what if we loop the other way around? So big loop, n equals 12. After the first 11 moves, we make a direct transfer from our previous vacant space, 16, to our new vacant space, 15. And we can see that this is the same as the last move in our sequence. Does this have n minus 2 interchanges, so 10 interchanges? Well, it does. Last step, step 3. Johnson says, after n moves, if the vacant space is again left vacant, so loop, we have an even number of moves. This is true because to return our vacant space to where it was, the number of left moves must equal the number of right moves, and the number of up moves must equal the number of down moves. If there's a left for every right and an up for every down, this is an even number of moves. N must be even. Nice, we understand all 3 steps. But what is actually being proved? Does Johnson say our impossible puzzle is actually not possible? Well, Johnson proves that any n moves, which is even, applies n minus 2 interchanges, which is also even. This means if there's an odd number of interchanges, and we can only apply an even number of interchanges, we can never reach 0 interchanges. If we can never reach 0 interchanges, we can never reach our solved board. So it's fair to say that this puzzle is actually not possible. But we can't celebrate just yet. Why? This is only half the story. Sure, we proved odd interchange puzzles are impossible, but what does this say about even interchange puzzles? I think they are possible, but do we know for sure? Let's prove it. A permutation is an arrangement of elements. The moves right, right, down, left, left, up describe a permutation. This permutation goes from 10 to 11, from 11 to 12, from 12 to 15, from 15 to 14, and from 14 back to 10. With 2-line notation, this is what the permutation would look like. The top row represents from, and the bottom row represents to. A much more practical way of showing permutations is cycle notation. 10, 11, 12, 15, 14 describes the same permutation. We go from 10 to 11, from 11 to 12, from 12 to 15, from 15 to 14, and 14 back to 10. Positions not included in cycle notation are unchanged. So we go from 1 to 1, from 2 to 2, from 3 to 3, and so on. Cycle notation is important because we can introduce our first special property. Every cycle can be written as the product of 2 cycles. 2 cycle just means a cycle of length 2. Okay, let's check if this is true. First, we go from 4 to 1, then 1 to 4, then from 3 to 1, 1 to 3, then 2 to 1, 1 to 2. Okay, our result is 2, 3, 4, 1. Cycle notation without the decomposition goes from 1 to 2, from 2 to 3, from 3 to 4, from 4 to 1. This is 2, 3, 4, 1, the same permutation. So, this cycle can be written as 10, 14, 10, 15, 10, 12, 10, 11. But wait a minute, why does this look familiar? A 2 cycle swaps 2 elements, kind of like an interchange. And our sliding puzzle permutation decomposed into an even number of 2 cycles. It seems similar to Johnson's proof from earlier, but it's not the same. Remember that interchanges swap adjacent tiles, while 2 cycles just swap 2 elements. They don't have to be next to each other. But what if they're saying the same thing? Every 2 cycle can be described with an odd number of interchanges. If the 2 cycle describes adjacent tiles, swapping them is 1 interchange. For each extra distance between tiles, we add 2 interchanges. Okay, let's say our cycle is 10, 15, so distance is 2 between them. Swapping them is 3 interchanges. And the 2 cycle 1, 15, which has 5 distance, swapping them is 11 interchanges. So this brings us to our first big conclusion. Each permutation can be described as a product of 2 cycles. Each permutation can be described with an even number of inversions. This was Johnson's proof from earlier. Each 2 cycle can be described with an odd number of inversions. And a collection of odd numbers that sums to an even number must be of even length. So, each permutation not only can be described as a product of 2 cycles, we know the product of 2 cycles must be of even length. Let's remember this for later. Our second special property of cycles is that all even length products of 2 cycles can be generated by the set of 3 cycles. What does this mean? Okay, for our set of 2 cycles, so we have AB, BC, and AC, it says for any even length product of 2 cycles, so AB, BC would be an example. This means we swap A and B, then swap B and C. Okay. AB, AB, AC, AB is another example, right? Even length, 4 elements. AB is not an example because it's odd length, and AB, BC, AC is also not an example. This seems like it is very hard to prove, right? There can be an infinite number of even length products of 2 cycles. But do not be alarmed. The way we show coverage is by showing that any additional pair of 2 cycles can be answered with our set of 3 cycles. So, there are 3 cases of 2 cycle pairs we could add. Case 1 is both elements overlap, so AB, AB. Case 2 is only the first element overlaps, so AB, AC. And case 3 would be only our second element overlaps. This would be AB, BC. Okay, case 1, AB, AB. We swap A with B, we swap A with B again. This accomplishes nothing. When nothing changes, we call this the identity permutation. Just remember it means nothing changes. Can we construct the identity permutation with our set of 3 cycles? The answer is yes. ABC, 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 made up of 3 cycles, is the identity permutation. We go from A to B, from B to C, from C to A, and we do this 2 more times. The result is we went from A to A, from B to B, from C to C. Nothing changes. Nice. So case 1, we match our additional pair of 2 cycles with 3 cycles. Case 2 is only the first element overlaps. So AB, AC. We swap A with B, we swap A with C. And the result is we went from A to C, from C to B, and from B to A. This is the same permutation as our 3 cycle, ACB. So once again, we have covered this pair of 2 cycles with our set of 3 cycles. Case 3 is only the second element overlaps, AB, BC. When we swap A and B, and swap B and C, the result is from A to B, from B to C, and from C to A. This is the same as our 3 cycle, ABC. So we cover all cases. Okay, with just 3 elements, ABC, we have shown that even length products of 2 cycles can be covered by the set of 3 cycles. But our sliding puzzle has 15 elements, so we need to show that adding an additional element still maintains this property. We have ABC, let's add some element D. Okay, we have the same 3 cases from earlier. Both elements overlap. ABAB is still the same permutation as ABC, ABC, ABC. First element overlaps. ABAC is still the same as ACB. Second element overlaps. ABBC is still the same as ABC, but introducing element D does give us one new case. What if neither elements overlap? So we can say ABCD. Can we construct this permutation with 3 cycles? Well, remember that from case 1, any 2-cycle product with itself, so ABAB, is the identity permutation. Because it doesn't change anything, we can add it wherever. ABCD is the same as AB, BC, BC, CD. Can we write it as 3 cycles? Yeah, because ABBC is the same as ABC, and BCCD is the same as BCD. So, ABCD can be written as ABC, BCD. Okay, let's double check if this is true. We start with ABCD. Let's apply ABC. So, from A to B, from B to C, from C to A. And the result is BCAD. Then, let's apply BCD. From B to C, from C to D, from D to B, and the result is BADC. BADC is the result of swapping A with B and C with D. So these are the same permutations. Nice. Adding an additional element maintains that we can generate any even length product of 2 cycles from our 3 cycles. Because it holds true when we add an element, we can keep adding elements. So we can say this property is true for all n is greater than or equal to 3. Okay, Last special property about cycles. We can create any 3-cycle from the set of 3 cycles in the form ABK. What does ABK mean? A and B are grounded elements, and K is just any other element. For example, if we have 15 elements, and we have the set of 11, 12, 1, 11, 12, 2, 11, 12, 3, all of them, we can create the set of all 3 cycles. There are 4 cases. Case 1 is 3-cycle has both grounded elements, so this would be ABK and AKB. Case 2 is 3-cycle has only our first grounded element, so this would be ACD, and remember that C and D are just any other elements. Case 3 is cycle has only our second grounded element, BCD, and case 4 is our 3-cycle has neither of our grounded elements, so CDE. Okay, case 1, our 3-cycle has both of our grounded elements. ABK already conforms to the form ABK, so we match it with itself. AKB, however, is not in the form ABK, so we need to construct some permutation that equals AKB. Well, one property of 3 cycles is that AKB is equivalent to ABK, ABK. But let's double check if this is true. Apply ABK from A to B, from B to K, from K to A. And do it one more time. In total, we went from A to K, from K to B, from B to A. This is AKB. So we have covered this case with 3 cycles that conform to ABK. Case 2 is cycle has only our first grounded element, ACD. Okay, let's remember our fundamentals. We can always decompose any cycle into a product of 2 cycles. ACD is equivalent to DACA. We can always add our identity permutation without changing anything. And our identity permutation can be any 2-cycle with itself. So DACA is the same as DABABACA. DABA is the same as ABD, and BACA is the same as ACB. So we have ACD is equivalent to ABD, ABC, ABC, where all 3 cycles conform to ABK. Case 3. Cycle only has our second grounded element. Let's use the same approach. So BCD, we first decompose into 2 cycles, DBCB, add our identity permutation as ABAB, so we have DB, AB, AB, CB. Combine into 3 cycles, BAD, BCA, and remember that we can always rearrange the order of cycles. BAD goes from B to A, from A to D, from D to B, so we can always rewrite this as ADB. In the same way, BCA can be rewritten as ABC. And finally, we can reuse our findings from case 1. ADB is the same as ABD, ABD. So BCD is equivalent to ABD, ABD, ABC, where all 3 cycles conform to ABK. Okay, case 4, last case. Neither of our grounded elements are in the cycle, CDE. This case looks different because there's no overlap with A and B, so how could we possibly construct this with ABK cycles? Well, do not panic, we can use the same approach. First, decompose it into 2 cycles, EC-DC. Then add our identity permutation, AC-AC. This gives us EC, AC-AC, DC. EC-AC is equivalent to CAE. AC-DC is equivalent to CDA. So all of this is equivalent to CAE, CDA. These can be rewritten as AEC, ACD. Case 2 showed us that ACD can be written as ABD, ABC, ABC. And we can use case 2 again. AEC can be written as ABC, ABE, ABE. This gives us the final substitution. CDE is equal to ABC, ABE, ABE, ABD, ABC, ABC. Is this actually true? Starting with ABCDE, let's try it out. Apply ABC, apply ABE, apply ABE again, apply ABD, apply ABC, apply ABC again. What is the result? A goes to A, B goes to B, and our only changes are C goes to D, D goes to E, and E goes to C. This describes the cycle CDE. With all 4 cases done, we have proved that the 3 cycles ABK can construct all 3 cycles. Okay, what are we even talking about? I thought this video was about sliding puzzles. Well, we are talking about sliding puzzles. If we can show that the 4 basic sliding puzzle moves can produce all 3 cycles ABK, so 11, 12, 1, 11, 12, 2, 11, 12, 3, we can use those to produce all 3 cycles. If we have all 3 cycles, we can produce all even length products of 2 cycles. If we have those, we can produce all solution permutations. So finally, let's complete the last piece. We construct all 3 cycles ABK with our 4 sliding puzzle moves. And we're going to use 11 and 12 as our fixed A and B. We can organize our moves as follows. Preamble Q tucks away 11 and 12. We don't want them mixed up with the other pieces. Long cycle R, this cycle determines what K is in our cycle 11, 12K. Permute P, which determines how many times we step through our cycle. And then inverse R, inverse is just the moves in the opposite order, and inverse Q. This puts all other tiles back where they were, so we only modify tiles in our cycle. Okay, let's look at some examples. How do we generate 11, 12, 10? Well, first note that 10 is 1 step away in our long cycle. So let's apply preamble Q, long cycle R, permute P, inverse long cycle R, inverse preamble Q. And the result is we go from 11 to 12, from 12 to 10, from 10 to 11, and all other tiles remain the same. This is 1 step through our 3 cycle, 11, 12, 10. But to show the entire 3 cycle, we need to be able to step multiple times through it. So let's apply Q, R, P2. 2 just means P then P again. Inverse R, inverse Q. And the result is we go from 11 to 10, from 12 to 11, and from 10 to 12. This is the same as stepping through our cycle twice. And QR, P3, inverse R, inverse Q, applies no change. This is expected because the product of any 3 cycle 3 times is the identity permutation. Nothing is changed. Very nice. We have constructed 11, 12, 10. But what about, let's say, 11, 12, 1? Well, let's count how many steps to 1 in our long cycle R. I count 6 steps. So, Q, R6, P, inverse R6, inverse Q, should step once through our cycle. We go from 11 to 12, from 12 to 1, from 1 to 11, it steps once through our cycle. Q, R6, P2, inverse R6, inverse Q, steps through it twice. And Q, R6, P3, inverse R6, inverse Q, applies no change as expected. So what have we created? By adjusting R and P, we have created all 3 cycles ABK. From all 3 cycles ABK, we can construct all 3 cycles. From all 3 cycles, we can construct all even length products of 2 cycles. From all even length products of 2 cycles, we can construct all solution permutations. It's done.